In this video, we're going to take a look at even and odd trig functions. Now, before we get into the trig function, all six of our main trig functions, and whether they're even or odd, we need to talk about what an even function and an odd function is. Let's start with some polynomials, and I'll graph something like y equals x squared, and something like y equals x to the fourth, and something like y equals x to the sixth. And I'm not going to highlight all these guys at the same time, so let me deselect some of these graphs. You notice that y equals x squared, we've got that parabola shape. Something interesting about that graph is it looks like it's symmetric about the y-axis. So anything on the left has a match on the right. Interestingly enough, I do that with y to the fourth, it's the same idea. Anything on the left matches up with anything on the right. If I do it y to the sixth, anything on the left matches up with anything on the right. So these are called even functions, and algebraically, really, the definition is this, that, well, geometrically, I should say. We'll get into the algebra in a minute. But geometrically, what that means is that there's symmetry with respect to the y-axis. Now, with polynomials, it's pretty easy because just look at your exponent. Now, again, we're assuming no kind of translation left or right or any kind of other transformations that could affect this. However, if we have an even exponent, we could say it's an even function because it's symmetric about the y-axis. Now, what if we have an odd exponent? What if we graph y equals x to the third? Now, things are a little bit different. You might expect that it would be symmetric about the x-axis, but that is not the case. Something interesting is going on here. Let's graph y equals x to the fifth. And these are all odd exponents I'm going to graph. Seeing kind of the same pattern. So let's go y to the seventh, or x to the seventh, see what happens there. Same thing. So what's happening here, and I'll go to x to the third to make it easier, is what we have going on here is symmetry with respect to the origin. So if I were to grab a value, let's say this one right here, so it's at roughly 1, we'll call it 1, 1, not a great value, but if I go to the other quadrant, if I go to -1, and I find the value there, it's about -1. So what's happening is that anything that's in this first quadrant has a mirror image in the third quadrant. So the symmetry is with respect to the origin. We're switching the signs on both the x and the y coordinate. Now that's typical of odd functions. Now that's great, but we're talking about trig. And there's no exponents really when we're talking about trig graphs. So how do we know which is which? Easiest way is to start graphing and see what happens. So I'm going to start with the most basic trig function that we have, which is sine of x. And so if I look at y equals sine of x, I'm trying to figure out what the pattern is, what kind of symmetry it has going on. Now, I immediately look at the y-axis, and I don't see a mirror image over this. But I am seeing a point here and here that are really, really similar. We've got pi over 2 comma 1 and negative pi over 2 and -1. What that shows me is symmetry about the origin because the x and y coordinates have both changed signs. So I would classify sine as an odd function. All right, what about cosine? This one's more interesting, I think, because it does have that symmetry about the y-axis. If I grab a point here and here, those are the same thing. The y-coordinate's the same, but the x-coordinate has changed signs. You can do the same thing over here as well. The y-coordinate's the same, but the x-coordinate has changed signs. That's an even function. What about the reciprocal functions? Let's start with the reciprocal of sine, which is cosecant of x. And as we would expect, it's got that same pattern that the sine does. Mirror images across the origin. So again, same values but different signs for the x and the y coordinate for a matching point. You can grab a point over here, right over here, same thing. Different signs on the x's and the y's, but really effectively the same value. So cosecant of x would be considered an odd function, just like sine. What about secant of x? Yep, it's got that symmetry. So again, splits right down the middle, that y-axis. So I can grab a point here and here. They're the same except the x coordinates have changed signs. So secant is an even function. The more challenging ones are the tangent and cotangent. Tangent's not so bad, although it's strange looking, but it kind of has that same pattern. So if we look at this graph right here, if I start with this, if I start grabbing a point here, let's say 1.327 and 4.02, I can find a matching point down here. Should be right click instead of left. That is pretty darn close. So again, same values for the x and the y, but different signs. So it's got symmetry about the origin. You can kind of tell in this area how it does that. Basically makes a linear equation. So tangent of x would be considered an odd function. And then finally, what about cotangent? Well, cotangent would follow a pattern. Let's see if this works here. And that might be difficult to see. But it is not an even function. So if we're looking here at the values up in this area, if it was an even function, I would expect it to approach this way as well. And it doesn't do that. What it does is approaches that negative direction. So I have a split going on. It's going up in this area and going down here in the third quadrant, which would make it, again, an odd function as well. So let's summarize this. Again, we're talking about all of our trig functions, not the other polynomials. They're not really as important right now for us. And then what does this mean algebraically for us? What do we do with this? So the even functions we said were cosine of x and secant of x. And all the others were odd. Sine of x, cosecant of x, tangent of x, and cotangent of x. Now, what this means, we have an even function. And I'm going to give you like the formal algebraic definition. If we took the value of a function and plugged in the opposite of the x value, what we would get is the same value as if we had plugged in x. So if I were to find the cosine of pi over 2, it should equal the cosine of negative pi over 2 because it's an even function. When I do the same thing with an odd function, though, f of negative x doesn't follow the same rule. What it does actually is switch the sign of the output. So if I find the sine of negative pi over 3, it'd be the same thing as the opposite of the sine of pi over 3. So let's formalize this. Let's put some examples to this. So if I were to find something like, let's say the secant of negative pi over 3. Based on our definition, our understanding that secant is an even function, what that means is it's going to have the same exact value as the, oops, I'm writing cosecant for some reason, the same exact value as the secant of pi over 3. So again, we just have to know that secant value of pi over 3, which is the reciprocal of the cosine of pi over 3, which would give us 2. So not only the secant of pi over 3 equals 2, but the secant of negative pi over 3 equals 2. What if I had an odd function? What if I took like the tangent of negative pi over 4? Based on our understanding of knowing that this is an odd function, I'm going to take that negative value and it comes out in front, and it really is written like this then. The opposite of the tangent of pi over 4. The tangent of pi over 4 we know is 1, so then this would equal negative 1. Now, you don't believe me, right? Maybe you're like, wait a minute, that doesn't make any sense. Or maybe you do believe me, good for you. But we can always verify these. What we could do is, because it's a negative value, knowing that this is the unit circle, I can actually do one of two things. I can turn this into another angle that I already know by adding 2 pi to it. So if I did that, if I added 2 pi to negative pi over 3, I get 5 pi over 3. And I know the secant of 5 pi over 3 is 2 because it's in quadrant 4, so I know it's going to be positive. And it's equal to, the cosine is equal to negative, or sorry, 1/2 there. Another way to think of it, instead of going in this positive direction around the unit circle, because it's a negative angle, we can go this way. So if I know I'm here, I can go that way pi over 3 until I hit the first one, 5 pi over 3. So there's a couple of approaches you can take. The official way we want you to know, though, is the even the odd function. So cosine and secant are even, which means that you effectively ignore the sign. It doesn't matter because there's symmetry about the y-axis. For the odd functions, you're going to change the sign of the function. Man, I got to be real careful. You're going to change the value of the function, whether it be positive or negative. So a tangent of a negative angle becomes the negative tangent of that same angle. That's what we're working with the even and odd functions.